Okay, hello everyone. So we are going to talk about chapter number 25, that's about the Gauss law, which is very important law in electromagnetism. So it states that the total electric flux through a closed surface is equal to the net electric charge enclosed by the surface divided by the permittivity of free space. That is, so it states that um, the the total electric flux through a closed surface is this. So this is E dot dA equal to Q over epsilon naught. So this epsilon naught is a permittivity of free space, and its value is 8.854 times 10 power minus 12 Coulomb square plus over Newton meter square. So this Gauss law can be used to solve for the electric field in a region of space if the distribution of the charge is known. Okay, so for example, to calculate the electric field of a point charge, so you have to draw or construct a Gaussian surface around the point charge like this, and the electric field vector will be perpendicular to the Gaussian surface and pointing away from the point charge. Okay, so like this. So the surface integral of the electric field over the Gaussian surface will be equal to the net electric charge of the point charge divided by the permittivity of the free space. So similarly, to calculate the electric field of a uniformly charged sphere, you can use Gauss law to construct a Gaussian surface that is a concentric sphere with the charged sphere. That is, like, if you have to calculate the electric field of the uniformly charged sphere, so you have to calculate the Gaussian surface like this and do the further calculation accordingly. So to calculate the capacitance of the capacitor, you can also use Gauss law to calculate the electric field between the plates of the capacitor. Okay, so let's say there are two plates of the capacitor and you want to know the electric field. Okay, and you can use Gauss law for that too. So it's a kind of powerful tool that can be used to solve a wide variety of problems. For example, so you want to find the electric field around a thin metal plate, so you can draw a Gaussian surface like this cylinder and do the according calculation for that. So let's try to solve the discussion problem. That's our focus to the chapter 25. So let's talk about problem number 61. So it says a rectangular plate with sides 0.60 meter and 0.40 meter long is lying in a XY plane, which I have drawn here. So this is the plate with length 0.60 meter and its breadth is, like, for example, breadth is 0.40 meter. So you will be able to find the area of this plate. Okay, so that will be uh, 0.60 meter times 0.40 meter. So if you want to write this in a vector form, so it will be directed to the z-axis. So that's why this is k vector, unit vector along z-axis. So altogether it will be 0.24 meter square along z-axis. So now you can use the flux through the plate. So flux is just E dot A. Okay, so the electric flux is denoted by phi and E on the subscript to denote the electric flux. So it's just a product of E dot product of E and A is area vector which we already calculated, and electric field which is the uniform electric field which is given. So that's E equals to 0 equals to minus 4 I plus 5 J and 3K. So this is the unit of electric field. So and the product of E and A, the dot product is, this is A. So when you do the product, the dot product, so you just have to do the dot product because all others are 0. So you will get 0.723 times 0.24 and k dot k, that's 0.72 Newton per coulomb meter square. This is the flux through the plate.